Okay, so let's look at the application problems for Module 5. As you know, we're going to have some out of Chapter 13, and that's actually the bulk of them. I think there's 5 problems out of Chapter 13, and then we're going to have 2 out of Chapter 17. It's just kind of one little section there. So let's just take a peek at each one of the problems so that you have an idea of what you're up against. So the first one that we have here is 13-139. This is found on page 879. It's actually going back a section, but it is an application of impulse momentum. So let me go underneath here. What we're looking at, it's right at the top of the page here. We have a baseball player that's catching a ball. And what we have going on here is the ball is coming in at 90 miles per hour. And it has a 5-ounce ball, so you have to convert that to the appropriate weight. And it says here that the average speed at impact is going to be 30 feet per second as it hits his glove, and he moves back 6 inches as he catches it, okay? Bringing that ball to a stop. Determine the average impulse force on that player's hand, okay? So again, the approach is going to be impulse momentum. Couple things to keep in mind. Notice that your velocity coming in here is 90 miles per hour. You want to convert that. Make sure you convert it to feet per second to be appropriate with our units. Additionally, you have a 5-ounce ball that is weight. There are 16 ounces in a pound, so you want to get that weight into pounds. And then lastly, the distance here is given to you that the glove moves back as the catcher is catching the ball, and you want to convert that to feet, so it would be 0.5 feet. That way, each one of your units are on the appropriate, units in order to get the right values out. So that's going to be your first problem. So again, 13-139, and that's in the section ahead of time on 879. The second one that you have, we did not do sample 13-17, okay? What I want you to do is follow that example along using the numbers that you see here. So even though they're going to have their own values that they're going to do there, you're going to differ in the package is going to be 22 kilograms. Your velocity 1 is going to be 8 meters per second, and the cart is going to be 45 kilograms. Follow the problem exactly, just using different numbers here. Okay, again, I didn't go over this one. I think it's one that's pretty easy to follow along to kind of, for you guys to kind of do and kind of discover yourself. If you have any questions, let me know. But that's going to be the second problem that you do. The third problem is going to be 13-155. Open up to that. And 157. These two are found on page 902. Kind of the top-ish here. So the first problem that you have is going to be 13-155. We have 2 steel blocks. Don't worry about friction on the horizontal surface, but immediately after they impact, their velocities are shown here right before impact. Knowing that our coefficient of restitution is 0.75, determine the velocities after impact. So you're going to have, if you would, a velocity A prime, a velocity B prime, and also the energy loss during impact. At the end of that previous problem, so at the very end of sample problem, was it 13? Did I say 13-17? It's going to have a section there where you have to calculate the energy loss. Use that for the energy loss at the end here as well. Okay, so it'll give it to you at the end of that example. So try to do these in order because that'll help you in this case. The second application problem on this page is 13-157. This is a tennis ball problem, kind of neat. It says one of the requirements of tennis ball is to be used in official competition is that when dropped onto a rigid surface from a height of 100 inches, the height of the first bounce must be between 53 and 58 inches, okay? You want to determine the range of the coefficient of restitution values that a tennis ball meeting those requirements is going to have, okay? So that is the second problem on this page. Then what we're going to do is we're going to go to the next page, and your next problem and your last problem, I believe, in chapter 13 is going to be a bumper car problem. So 13,163 is what you're going to be doing for your application problem. This is very similar to the packages on the conveyor problem that we looked at. You're going to have to kind of do two at a time, even though you've got three cars here. And you want to find, I'm not going to read the whole thing, but you want to determine the velocity of car C so that after car B collides with C, the velocity of car B is 0. So it comes back to a stop. So A is going to hit B, C is going to hit B. And then what does C have to be in order for B to be 0? Okay, kind of an interesting look at this. So the problem that we did with those packages on the conveyor will help you with this process. Be aware of, and this is sometimes one of those problems where you might not be always confident in the direction of the velocities. So what I suggest that you do, just assume positive direction for everything. And then that way, if you get a negative as a final answer, you know that you need to make that velocity the opposite direction. Does that make sense to everybody? Okay. So that's how I kind of deal with when I'm not sure about directions. I let my math kind of figure it out for me. So that is problem 13,163. Then you're going to be shifting gears and you're going to be going to the last two problems, which are in chapter 17. And the two problems that you have here actually deal with the same illustration. You're going to be doing 1755 and 1756. In both cases, you're going to be putting a moment, if you would, around a shaft that has a block or a cube on the end of it. This is where the moment of inertia for a cube is going to come in handy. I put that on that equation sheet for you guys for these two problems, okay? So the first one, you're going to be determining the magnitude of the couple M to get the final angular velocity of the system to 960 RPM within 4 seconds. And then the second problem here is you're going to have to determine the time required for the angular velocity of the system to increase from 1,000 RPMs to 2,000 RPMs. Okay, so in this case, you have a W1, if you would, and then you have a W2, so a before and an after. A lot of times we start from rest and our W1 is always 0, but in this case, it would be 1,000 RPMs. Remember, RPMs wise, you have to convert those to radians per second to use it in the equations that we looked at. Also, any lengths, make sure that they're in the appropriate units as well. If they're called out in millimeters, make sure you convert those to meters. If they're called out in inches, convert those to feet. And probably worth noting here is that at 1755 is standard or English units. So when you're given pounds, that you have to convert to mass by dividing by 32.2 rate of gravity. But in the metric problems, they're giving you kilograms, so you don't need to convert. You can use the values for kilograms that they give you respectively here. Okay, so that really rounds out kind of an overview of the items that you're going to be looking at for your application problems. So, so the rest of the time here, you have to work, and then I'm available to answer any questions that you might have. So, so I will stop the recording.